Greetings, Chemistry 1A. In this recording, I'm going to be reviewing a specific problem from the 8th edition of our textbook, specifically problem 4-131. Perhaps you might want to get your textbook out to review that problem before we get started. If this is not problem number 131 in the 9th edition, it is one of the problems, but I think it's number 131, so you might want to look that one up. I'd like to point out that this problem, I like it very much because it incorporates just about everything from chapter number 4. It incorporates the idea of solutions and their concentrations. It talks about oxidizing agents and reducing agents, talks about oxidation and reduction, which are, of course, very much one and the same. How to balance oxidation reduction reactions, talks about titrations, and ultimately how to do the calculations associated with titration. In addition, there's some rather interesting algebra associated with this. So bottom line, again, I think this covers just about all of chapter number 4 in one problem. Now, if you're looking at the problem and wondering how in the world are you going to solve it, that's understandable. It is a very complex problem, and I have no expectation that I could give you a problem such as this on an exam setting. It's just way too many things going on for me to do that. However, as I walk through the problem, I'm going to point out at several points the types of things which you do need to know for the exam. So kind of keep all of that in mind. So here we go. I'm going to share screens and show a few things. Okay, so I'm screen sharing. Give me a moment. Of course, I don't want to end meeting. I want to show this screen. So before you start watching the video, I would like you to watch this YouTube video on a titration of permanganate and oxalic acid, which is very much like the titration I'm going to describe a little bit later. Here is the direct link or direct URL. Unfortunately, this is not clickable in the Zoom setting, so you just have to type it out directly. Or if you go into YouTube and search this string of words, you'll likely come up with the same one. It is an 11-minute video or so on titrations. I'm going to click on this so that you can see how it starts. And I'm not going to play the whole thing for this recording. You can see it's about a 9.5-minute video. So there's the video that I would like you to go into separately to look at.
Determination
So
of concentration.
Close that and stop that. So again, take your 10-minute break right now and watch that video. Perhaps pause this video and I will close that. Okay. Since you're back, I'm assuming that you have watched that video. And I'm going to read the problem to you. It helps me a little bit. And it says, mixtures of calcium chloride and sodium chloride are used to melt ice. That is true. We learn about that in Chem 1B, about why salt solutions tend to lower the melting points. But again, that's a Chem 1B topic. And frankly, that first sentence has nothing to do with how you solve the problem. It's just background information. It says a dissolved 1.9348 gram sample of such a mixture, that is to say a mixture of calcium chloride and sodium chloride, was analyzed by using excess sodium oxalate to precipitate the calcium 2+ as calcium oxalate. So what that means is that this mixture was reacted with sodium oxalate being a very soluble substance. Again, solubility rules tell us that sodium salts are soluble. So the solution was reacted with sodium oxalate. The calcium chloride precipitates as calcium, or forms a precipitate of calcium oxalate and sodium chloride. That is, I've got my sodium here and my chloride there, so I got 2 sodium chlorides. Notably, sodium chloride does not react at all with sodium oxalate. Everything is completely soluble. There's nothing forms a precipitate. So in effect, what this reaction does is allows us to form the precipitate of calcium oxalate. And later on, we're going to see how doing that lets us determine how much calcium must have been in the original mixture. So that's what that second sentence in there says. It says that calcium oxalate, I've got it written here, was dissolved in sulfuric acid, and the resulting oxalic acid was titrated with 37.68 milliliters of 0.1019 molar potassium permanganate. So what that reaction is saying is that the calcium oxalate is reacted with potassium permanganate in the presence of acid. So the addition of that sulfuric acid was just to ensure that we had a sufficient supply of hydrogen ion in solution. Recall from earlier, I said that the products of an oxidation reduction reaction, of which this is an oxidation reduction reaction, are dependent on conditions, and at least for Chem 1A, I am not expecting you to know what the products are. So here I'm telling you, the products of this reaction in an acid solution are carbon dioxide and the manganese 2+ ion. We will balance this reaction in a minute. So given all of that information, the question then goes on to ask for balanced and net ionic equations. It asks what the oxidizing agent and what the reducing agent are, and ultimately to calculate the mass percent of calcium chloride. Now, I had to stare at this a bit. It's not immediately obvious, perhaps, what it's asking you to do. So I've created a plan that I'm going to walk through. Ultimately, then, this is where we want to end up. Okay, what's the plan? How am I going to go about this? One, I am going to balance the oxidation reduction reaction using the method that I presented in class a couple of nights ago. Note that I have posted this file in the file section on Canvas for how to balance it. So you may want to go there as a reminder. And then after that, I'm going to determine the moles of oxalate. Oops, pardon me, that should be a 2- right here where my cursor is at. Shame on me. I'm going to determine the moles of oxalate that were titrated in the oxidation reduction reaction using the balanced equation and this information on concentration and volume. And then I'm going to determine the moles of calcium 2+ that were in the calcium oxalate. I'm going to determine the moles and mass of calcium chloride because I need that so that I can determine the percent of calcium chloride in the overall mixture. And along the way, I'm going to ID the oxidizing agent, reducing agent, and the oxidizing and reducing reactions. So that's my plan. Having that as my plan, then let me get to work doing just that. Okay, here we go. So I said that we would start by determining the balanced equation. So here we go. This whole piece is the oxalate ion. It is not something that we've talked about in our nomenclature rules, and simply don't worry about it. It's just not something that we're going to worry about. Calcium oxalate and potassium permanganate react. Note that the calcium ion and the potassium ion are going to be spectator ions. They're there before and they're there after. So in a minute, I'm going to kind of set them aside and ignore them. The products of the, so having ignored them, I can add them back in later, knowing that they are spectator ions. This really comes down to the reaction of the oxalate anion and the permanganate anion. So let's balance that equation. And using the steps that I talked about in class and using the steps that you can find on the file that I have posted. They start off here. Step 1, determine the products of the reaction. Well, as I said just a little bit ago, the products of the reaction, let me get them there in a moment, are carbon dioxide and manganese 2+. I want to diagram this reaction before I go on to balancing it. So this step right here represents oxidation. The carbon is going from an oxidation state of +3 to an oxidation state of +4. That is loss of electrons. That is to say, that's how the oxidation number increases, because it has lost electrons. So this step is oxidation. So again, as I said, this problem is too difficult to put on an exam, but this idea of being able to identify oxidation and reduction is, of course, not. This step, the manganese is going from +7 to +2. The oxidation state is the same as the charge in this case. The number is going down, that is reduction. It is going down because it has gained electrons. So that is reduction. The thing which, so if this is oxidation, the thing which brought about the oxidation is the oxidizing agent. This is being reduced. The thing which brought about the reduction is the reducing agent. Okay, so being able to diagram a reaction wherein you recognize oxidation, reduction, oxidizing agent, and reducing agent is, again, one of the key ideas and key concepts. Now, let me proceed then to continue to balance the equation. So the second step, the first step being identifying the products, let me put in there that this is occurring in an acid solution, is to balance, to separate the half reactions. There we go. And the permanganate and by half reactions, I mean the half reaction wherein oxidation occurs and the half reaction wherein reduction occurs. Step number 3, balance the elements other than oxygen and hydrogen. Well, in this case, again, ignore oxygen. I'm balancing the elements other than oxygen and hydrogen. I see I've got 2 here. I've got 1 here. So I'll go ahead and grab a different color. I'm going to put 2 there. Here, there's 1 manganese. There's 1 manganese. I don't have to do anything. Step number 4, balance the oxygens by adding water. And again, you'd say, well, where's the water coming from? These reactions, as you saw in that titration, there's water everywhere. So there's plenty of water to be had. I have 4 oxygens. Over here, I've got 4 oxygens, right? 4 here, 2 times 2 is 4. So I don't need to do anything here to balance oxygens. I come down here, I've got 4 oxygens. I've got no oxygens on the right. So I add 4 waters. Now I balance the hydrogen. Well, again, I look at this reaction, there is no hydrogen to balance, so I don't have to do anything. In this reaction, I note that I have just added 4 times 2 is 8 hydrogens. So I'm going to come over here and balance those hydrogens by adding H plus. There. At this point, we say the reactions are balanced with respect to mass. I'm going to go ahead and change this to black, oops, as that seems to be the color I'm doing everything in. So let me change that just a bit. Pardon that, solid point 2. There we go. Just lost that somehow. Okay, we say these reactions are balanced with respect to mass. There's the same number and types of atoms. However, if I look here, on the left, I have a -2 charge. Over here, I've got no charge. So I'm going to balance that by adding some electrons. Here, I've got a total of 8 times 1 is 8 plus, right? 8 plus and -1. Over here, I've got 2 plus, right? So the way to balance these charges is to add, how many am I going to add? 5 electrons, right? So 5 plus -1 plus 8 plus is in total 2 plus on this side. Over here, it's 2 plus. So I'm going to add 5 electrons. We now say the charges are balanced with respect to both charge and mass. But I have to put the two back together because while on paper I can separate them, the reality is the reactions have to occur in a homogeneous solution. So this is where I go to the least common multiple. The least common multiple of 2 and 5 is 10. That is to say, I need to multiply this reaction times 5, this reaction times 2, so that as this reaction occurs and gives up 10 electrons, this reaction will occur twice and use up those 10 electrons. So as I go down to this next step, I'm going to balance this. And I get 5 C2O4 2 minus plus 10 electrons plus 2 MnO4 minus plus 16 H plus. That's everything on the left side reacts to form 5 times 2, 10 CO2 plus 10 electrons plus 2 manganese 2 plus 8 waters. So there's the balanced equation. I'm going to cross off the 10 electrons because they occur on both sides. That's the balanced equation. Now, I want to remind you that these waters that are produced, right, they're produced into a solution which is predominantly water, so they in effect become lost. They really are of no particular consequence. The hydrogen ion, remember this reaction occurs in sulfuric acid, and you saw in the titration, as they started, they added a significant amount of sulfuric acid. They didn't go through the calculations at the time, but the sulfuric acid that was added was in significant excess so that they need not worry about consuming all of the sulfuric acid. The important points of this reaction are there is a ratio of 5 oxalates to 2 permanganate in the balanced equation. We're going to use that in a bit. Now, the other thing that I want to do is remind you that that before I started this, I removed the calcium and the potassium because I knew they were spectator ions. I want to put them back in now And if this step bothers you a little bit, it'll probably become much clearer later on that it really is a minor point. Excuse me, MN, not MM. Yeah, we'll go ahead and put these 16H plus in there. And again, as I said, they will be of no particular consequence, as the water will be of no particular consequence either. 10 carbon dioxides plus 2 MN2 plus 8 H2O. There we go. There is the total balanced equation for that particular reaction. I've got one minor adjustment that I want to make. The equation isn't quite balanced because I've got to add in the calciums and potassiums back into the equation. There we go. But as I said, the important points of this are going to be this molar ratio between the reacting systems. So that's what's going to be important as we do our stoichiometry in just a little bit. Okay, so what's the next part of our plan? So that was the first part, to balance the oxidation reduction reactions. The next part is the stoichiometry, the titration problem. And that problem is what I need to determine the moles of oxalate that were titrated. So let's take a look at diagrammatically how this would look. The YouTube video does a better job of describing a titration. So you're just going to have to live with my depiction here. So that represents a Erlenmeyer flask. And into the Erlenmeyer flask went the solution that had the calcium oxalate. So the calcium oxalate goes in, which is a source of oxalate ions, and then the titration occurs. That represents a stopcock, and it is filled with the potassium permanganate solution. The potassium permanganate solution, as previously described, is of that concentration, and VI, V initial, and V sub F. So the reaction starts off, remember, I don't have a purple pen, so the reaction starts off, the potassium permanganate is purple, and at the end of the titration, this solution became purple, indicating that we had reached the end of the titration. The difference between the initial and final volume was a total of 37.68 milliliters. And so therefore, that is the amount of potassium permanganate necessary to react quantitatively with the calcium oxalate. And again, the important pieces here are the permanganate ion and the oxalate ion. So now I'm going to walk through the calculations using this information to determine the number of moles of oxalate And later on, we'll see number of grams. But let's worry about finding the number of moles of oxalate. So we stare at this for a moment. Maybe you just paused the video and came back and are now looking at it again, wondering how we do this. Well, there are as many ways to solve this as there are to algebraically solve linear equations. I recommend to you that in most cases, when you're trying to solve a stoichiometry problem, specifically a titration problem, start with the known information. Right? This is the information that is known to you and will give you the amount of permanganate. So here we go. Converting from milliliters to liters just by moving the decimal place 3 places. It has a concentration of 0.1019 moles of potassium permanganate per liter. And from our balanced equation, right, there's our balanced equation, 5 moles of C2O, pardon me, I've been using calcium, so let me do it that way. 5 moles of calcium oxalate reacts with 2 moles of potassium permanganate. So this tells us, do the arithmetic here. Let me get my calculator out. And I get a value of 0.0096. Let me carry an extra significant figure. Nine, 5, 9, 9, 0 moles of calcium oxalate. I am carrying one too many significant figures. I'll round things off later, but I will point out that titrations tend to be a rather precise technique. And so anytime you see a titration done, you should be thinking precision and significant figures. So this gives us the number of moles of calcium oxalate. It's easy at this point in the problem to forget kind of where we've come and gone. This tells us the number of moles of calcium oxalate, and so therefore the number of moles of calcium chloride, because all of the calcium oxalate originally came from the precipitation with the calcium chloride. So ultimately, this is going to lead us to the number of moles of calcium chloride, and I think that is my next step. Yep. So if I have 0.00959990 moles of calcium, oops, no 2 there, oxalate, this seems like a trivial conversion, but that's okay. That many moles of Ca2 plus per mole of calcium oxalate. Pardon me, slight error here. Let me correct it now. It is 1 mole of calcium chloride that forms from 1 mole of calcium oxalate. That goes all the way back to the very initial part of the question. And if I continue on, let me just continue right on down here. There are the molecular weight of calcium chloride. Calcium, gotta look that up. .08. The chlorine is 35.45 times 2, 70.90, for a total of 110.98. So there are 110.98 grams of calcium chloride per mole. So this tells us, if I stop doing the calculation right there, actually I think I will, this tells us the number of grams of calcium chloride that must have been present in the very initial sample. Let me do that calculation right now. And I get a value of 1.0653 grams of calcium chloride. We're almost there, because the question that was asked was, what is the percentage of calcium chloride in the overall sample? Well, 1.0653 grams calcium chloride in a sample size, pardon me, that number was 1.9348. And of course, we multiply by 100 to get to percentage. And that equals 55.060% calcium chloride. Okay, there's a problem. Let me check to make certain I got the answer the book has. That's not a guarantee that I got it right, but generally speaking, if there's an agreement between the value you get and what the book has, it's a pretty good indication you've gotten it right. I will point out that even with the 9th edition of the text, there are occasional errors that crop up. So sometimes if you get an answer different than the book, it's possible that there's a error in there somewhere. So, pardon me, for number 131, and in fact, 55.06% mass calcium chloride. So in fact, I did get the exact same values the book had, which is comforting. It means I likely did not make a mistake. So again, I want to scroll through some of this again to point out some of the things in here which are elements of chapter 4. 1, let's see, recognizing, oxidizing, and reducing agents. Oops, it looks like I lost some of my lettering. Maybe right, oxidizing, pardon me. Recognizing oxidation and reduction, right? Oxidation is the loss of electrons, reduction is the gain of electrons, and oxidizing agents oxidize other things, reducing agents reduce other things. So that is, again, a key element: oxidation, reduction, balancing equations, etc. This process for balancing oxidation reduction reactions. I stepped through everything. You can anticipate a similar type of problem on the exam wherein you're asked to balance an oxidation reduction reaction. The other key thing here in the entirety of chapter 4 is titrations. And this is just one way that a titration problem can be set up. But these titration problems rely on the idea that you understand that a given concentration I've got there and volume are a way to determine number of moles. Up through chapter number 3, the way we determine number of moles, this is the problem, or the wording of the problem simply gave you the mass in grams from which you use molecular weight to determine moles. Here, we're giving you slightly different information, but ultimately you needed that information to get to moles, and then you used the balanced equation to do whatever conversion was necessary. And then this last part, frankly, was a little bit of a twist to determine percentage composition, but that's just an application of the particular problem. There we have. Please note in Canvas what what it is that I wanted submitted for this. Hopefully you read it beforehand. But in any event, what I want submitted for this has been noted in Canvas. See you in class.